This video is going to go over Euler's formula and cross-sections. We're going to begin with what is a polyhedron. So a polyhedron is just going to be a 3D figure whose surfaces are going to be polygons. Each polygon is going to be called a face. An edge is going to be a segment where two faces are going to intersect. And lastly, a vertex is going to be a point where three or more edges intersect. Okay, moving into Euler's formula, we have Euler is a Swiss mathematician who discovered a relationship among the number of faces, vertices, and edges of a polyhedron. Euler's formula is going to just be F plus V equals 2 plus E, where F is your number of faces, V is your number of vertices, and E is your number of edges. There is a little note here that when we start to talk about two dimensions, so for example, a net, Euler's formula is going to reduce to F plus V equals E plus 1, where in this case, F is going to be our number of regions formed by V, the vertices linked by two segments. And lastly, before we get into our practice problems, we have cross-section. A cross-section is going to be the intersection of a solid and a plane. You can think of a cross-section as a very thin slice of the solid. So down below, we're going to move into our first problem where they're asking us to list the vertices, the edges, and the faces of the polyhedron. So let's look and see what we can come up with. So I'm going to start off with our vertices. So remember, our vertices are going to be the points. And so here, if we look, we are going to have a point here at A, E, D, B, F, and then lastly, we have C. So I'm just going to name those points. Remember, when you're naming a point, you just write the capital letter, and that's all you need. Then let's move into our edges. All right, so our edges are going to be our segments that are going to be formed where the two faces are going to intersect. So an example here could be from A to B. That's going to be an edge. Then we have B to F, F to C, B to C, C to D, E to F, A to E, and lastly, we'll have E to D. So the key thing is, now that we know what our edges are, is just making sure we name them correctly. It's a segment, so we're going to have a line with no arrows above it. So let me list them off here. So we'll have AE, ED, AD, AB, EF. We have CD, BC, FC, and then BF. All right. And lastly, we have our faces. Okay, so our faces are going to be the polygons that we see. Those are going to be the two triangles and then our three rectangles that we see here. So for my triangles here, I'm going to just draw a little triangle in front. I'll use the three vertices, so A, E, D to name it. And then for the other triangle, I would have B, F, C. Moving into my rectangles, I would have a rectangle that's got A, B, C, D. So like I did with my triangles, I'm just naming the vertices that's creating it. I then have A, B, F, E. And then my last one would be, we can say E, F, C, D. Okay, so moving into number 2, we have for number 2, find the number of edges of a polyhedron with 6 faces and 8 vertices. So we're going to be using Euler's formula here to clarify, because of this term polyhedron they have provided us with. We know we're going to do the 3D formula, which is my F plus V equals E plus 2. I'm going to plug in. For my F, we have 6 plus my V is going to be 8 is equal to E, since I'm trying to find it, plus 2. Using my algebra, I can get 14 is equal to E plus 2. And when I subtract the 2, I'm left with E is equal to 12. So pretty simple. Now let's look at number 3. So for number 3, we have consider a net for the polyhedron in question 1 above. Answer the following. So they're asking to start off the number of regions. So remember, regions is going to be like our faces, but since it is 2D, it's going to just be the polygons, the flat surfaces. We've got, for example, we have 1, 2, 3, 4, 5 regions. Then we were asked about our vertices. So remember, the vertices is going to be those points. And so for here, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So because this is a net, we are going to have some multiples because it's being laid out, and that's okay. You can still count them out each time those lines are intersecting to form that vertex. We are going to count that as a new one. So we've got 10 here. And then lastly, we're asked about our segments. So I'm going to put little dashes on them just so that I know which ones I've already counted for. Don't think that I'm saying they're all congruent. I'm just making sure I'm counting them. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Once again, I am not saying that these are all congruent to each other. It's just making sure I don't double count or, miscount by missing a side there. So those are going to be my 14 segments they're asking for. All right, so now let's move into our next 3 problems where we're going to start to talk about our cross sections. So I will say for some people struggling to visualize cross sections, a good place to visit for help is going to be GeoGebra. They have a lot of resources that you can kind of play with it to see what a cross section is talking about, especially if you're struggling. For this, I'm going to try and do my best to help explain, but especially if you are one of my kids, please visit that link and look over to get an idea to help you out with that. So we have here, identify the cross section for the figure and the directions listed below. They're asking us horizontally and vertically. Okay, so we have a cylinder here. And what they're saying is if I were to take a plane, so I'm just going to draw, a little plane here, slicing through it. It's not going to be perfect. I want to know what shape am I going to see when I look at it. Okay, so a lot of the times what's going to be very helpful is to look at the shapes that kind of run in the same direction that are parallel to the plane that I've just drawn. So here, when I draw that plane through the figure, I will see that these circles, okay, on the top and on the bottom here are running parallel to that plane. So that means that here, in between those two circles, I should be able to have a cross section of a circle. So that's going to be my horizontal answer. Now, vertically, that can be a little challenging with a cylinder, with the idea that I just kind of covered. I'm going to real quick just erase what I have. But once again, drawing a plane to run that direction, we have that vertically. Okay, I'm going to see here, just kind of focusing in on these key points where I have intersected that cylinder. I'm going to see that I'm going to get the shape of a rectangle being formed. So, sorry for the sloppiness of that. This is going to be a rectangle for my vertical. All right, so moving on to number 5, we have identify the cross section for the cube in the directions listed below. So let me see what we had first. We have horizontally, vertically, and then diagonally. So once again, using that same idea, we've got our horizontally. So if I were to draw a plane through here, running horizontally, like I said, use the bases or the faces that you see that run to be parallel to that to help you identify that shape. Well, this is a cube. They did mention that. And so since this is a cube, we know that all of my faces should be a square. So my answer is just going to be a square. Which, applying that same idea for my vertically, so once again, let me erase real quick. If I were to draw a plane running vertically through this cube, like I said, think about the faces that are running to be parallel to it, those shapes. And here, once again, it should be a square since, as I mentioned before, all of my faces are going to be squares. Now, the one that was kind of confusing for some kids in class was the diagonal. So a lot of y'all kept with that pattern. We had square, square. You said we were going to have a square. But if I were to, through my vertices here, diagonally slice through this figure, some of you might be able to already tell what the shape is going to be, but it is a rectangle. And let me explain why. So remember, on a square, okay, so if I were just to have a regular square here, all of your sides are going to be congruent. But here, when I'm slicing through diagonally, I'm using this diagonal length in my cross section. And if you know, the diagonal length on a square is going to be slightly larger, because if you go back to your ratios for 45, 45, 90, you have S, S, S root 2 for that diagonal. So that length is going to be longer than the other sides. So that's what's making this into a rectangle rather than a square. All right, our final problem, number 6. Once again, we're going to identify the cross sections going horizontally and vertically. So drawing once again my lovely horizontal plane here. For some of you, you just need that quick visual to see the direction, to now find the faces that run that direction. Here, it's going to be my pentagon because I'm going to have 1, 2, 3, 4, 5 sides. So that's going to make this a pentagon as my cross section. And then moving vertically, let me erase one last time. If I were to draw that plane, okay, I can see that running that direction vertically, I'm going to have my rectangles. And so my cross section for the vertical is going to just be a rectangle. All right, hopefully this might have cleared up a little bit if you were struggling with your cross sections or Euler's formula. If not, like I said, definitely check out GeoGebra. But keep in mind with the cross sections, especially with the horizontal and the vertical, try and identify which of your faces run that direction. That will definitely help you identify the figure, the 2D shape that you should be seeing through that cross section.